Okay, everyone. Up next, we have Thibault and Arnold. They're going to talk about printing, 3D printing Martian spacesuits.
All right, so good afternoon, ladies and gentlemen, and thank you for being with us this afternoon. My name is Thibault, and this is my friend Arnaud. We are both students at the École Polytechnique, which is the French leading engineering school. And last year, during our senior years, we have been asked to do a team-based scientific project during 1 year. And the goal was quite simple: form a team and make something innovative. And we figured out that it might be interesting to try to do our own 3D printed Martian spacesuit. At that moment, we had no books, no money, no documents, no tutor, almost nothing, but still we managed to find 5 other guys crazy enough to join us on this amazing journey, and we quickly began to draw our first pattern.
So, for such a project to become a reality, you need a strong support, strong financial and a strong technical support. You also need someone which is specialized in spacesuits to drive you during the project. Basically, there are not so much people like that in the common state, but it was a difficult task. But eventually, we heard about the smart society, and the president of its French chapter, who has already built several analog spaces, kindly accepted to become a tutor. We also convinced our science board of the École Polytechnique to help us by giving us grant. And after a deep space exploration of the NASA archive, we gathered several documents, several useful documents to know, for example, how to pull down an astronaut, or what is the minimum mobility required for field exploration.
All right, so the very first thing that we did to build our spacesuit was to determine what type of spacesuit we would actually do. If you make a comparison, there is roughly 3 different types of spacesuits. On the right, you have rigid spacesuits, such as this prototype from NASA. This is one of the most reliable, the strongest one, but they are also extremely heavy, so not really good for field exploration. On the other hand, you have soft spacesuits, like this one used for the Apollo missions. This spacesuit gives you the best possible mobility, but they are not strong, not reliable enough for long Martian exploration. So we decided to do something in between with a semi-rigid Martian spacesuit, which means a spacesuit based on a rigid torso, which is the central piece that you see, and the limbs are protected with many different layers of fabric. So at that moment of the project, we started to talk to scientists, engineers, researchers, and even one astronaut to have the feedback about it. And they all had this simple question that you might be asking yourself at the moment: why? Why are you doing that? And by this, they meant 2 things. First, making a spacesuit for making a spacesuit is, well, a lot of fun, but not innovative. And then they showed us that there is actually a lot of different types of spacesuits made by space agencies, companies, students. So we figured out that we had to do a better check, a sort of double state of the art, if we wanted to have solutions for that problem.
So we did a double state of the art of the spaces in order to
Excellent.
have a better view of the current space world. And so on the one hand, they are student-made analog spacesuits, which are not pressurized, but simulate very well the fields inside the spacesuit. On the other hand, they are functional spacesuits, which are made by the space agencies. Such as the Z2 from NASA. decided that our rigid torso will be fully printed.
Yes, the choice of 3D printing is not a random choice because this is a quite recent technology not used yet in the field of spacesuits, and it allows you to build suits directly on Mars, but also to repair and maintain them easily, and even to recycle them. For instance, if you have a tall astronaut for crew number 1 and a small one for crew number 2, you can recycle the plastic or elements from the first spacesuit to make a new one for the second one. So this is actually an interesting technology. We decided to follow the following bill of specification. Our main goal was being to survive 30 minutes on Mars, which is not that much for field exploration, but still already quite a lot, right? So we had the following requirements. Basically, we needed to resist to the particular Martian atmosphere and provide the astronaut with a good internal temperature, oxygen. Of course, if you want to do field exploration, we don't go to Mars to be a cactus, so you need sufficient mobility and a minimum of electronics and tools just to give you enough safety and elements for a field mission. So this is a very difficult problem, of course, with thousands of solutions, and this is the one that we obtained. It's not perfect. Once again, keep in mind that it's a student project, so with student skills and student means. But still, we think that we found a few interesting solutions, and this is what we'd like to share with you today.
So as we decided to make a semi-rigid spacesuit, the first part to design was a rigid torso. This is a critical part because the rigid torso has to be made to measure in order to allow mobility. So we took about more than
100, yeah.
On Thibault, and we recorded these measures on the computer, and we did the 3D mannequin on the computer. Also, as we wanted to avoid the contact with Martian dust and to allow an easy access to the spacesuit, we designed this door, which is designed to dock outside the space habitat. In order to know whether or not the rigid torso would resist an internal pressure of 0.3 bar, we also did several tensile testing, traction tests with different samples of plastics. And we put the resulting data into the computer to simulate the pressure on the rigid torso until we found the best compromise between mobility and pressure resistance.
All right, so after 2 or 3 months of designing, we obtained what we thought were quite nice 3D files. And we thought that we would just simply send them to a private company, pay them, and then we would receive the 213 PC that we needed to obtain the spacesuit. But this was too expensive for our student budget. So we decided to do something different. We bought 4 3D printers, we assembled them and calibrated them ourselves, and we began to print our species. To obtain all the elements, we needed roughly a cumulative of 1,500 hours of cumulative printing, which represent around 40,000 feet of plastic filaments. So, oops, sorry. As you can see here, this is quite a lot of plastic. And then we put all the elements together with epoxy glue, which is particularly resistant in order to have the big elements that you see here. So this is for the rigid torso. When it comes to the different layers of fabric, we needed 2 things. First, mechanical protection from the outside environment, and then thermic protection. For the mechanical aspect, we decided to use these 5 different complementary layers. Polyester for comfort, nylon coated with urethane for air tightness, PLA is the plastic that we chose, Kevlar to resist all the rocks because on Mars they are cutting like razors, and Dralon, which is a special white tissue really useful against radiation and Martian dust.
So that was for the mechanical part. In order to know the temperature inside the spacesuit, we did a computational simulation according to these fabrics. So here you can see in green it's the body of the astronaut. The different layers of fabrics are represented by the gray elements, and in white it is the Martian atmosphere. So here you can see the temperature curve through the degrees Celsius. So the astronauts need to be cooled down. So that's why we produced liquid cooling and ventilation garment. Currently, in space agencies, they use the technology. They use water membrane evaporated systems, which works quite well in space, but unfortunately, it does not work on Mars because of the low pressure of the atmosphere. So we decided to do a more basic liquid cooling and ventilation garment.
Sorry.
Which relies on ice cartridges placed in this tank for the cooling system.
Right. One of the particularities of a pressurized spacesuit compared to a simulation spacesuit is that it is airtight, so if you don't want to die quickly, you need a breathing apparatus. This element is one of the most difficult elements to make in a life-supporting system. So we decided to do something quite simple by using a firefighter breathing apparatus. The idea is the following. The astronaut breathes directly inside the bottle, expires inside the envelope of the spacesuit, and then a mechanical valve will open to release the polluted air outside. So this solution, we were not satisfied by it at first, because we thought it was like too simple, but by looking in the archives of NASA, we found out that we had reproduced the solution that the American engineers used in 1953 to make the very first American spacesuit. So actually we went back to basics.
On the left arm of the spacesuit, we added an electronic display control module. Which links all the different parts of the spacesuit. So, for example, the SVG or the safety sensors. So the astronauts can monitor and can control the temperature, the oxygen level, the pressure inside the spacesuit, thanks to a joystick and an LCD screen. We also add several features which are quite useful for field exploration. So, for example, there is a laser limiter.
All right. So when we put our electrical wiring together, we obtain this. And well, the principle is the following. You obviously don't want to know all about it, and me neither. But the principle is the following. Here you have a battery, a 12-volt battery with a general switch, which allows you to isolate the battery from the rest of the system in case something happens. This battery gives power to a pump for the liquid cooling and ventilation garment, and to two different electrical devices which will allow us to have different tensions inside the spacesuit with just one battery. Then we simply use an Arduino electronic card with different captors, the joystick and the LCD screen, and after a little bit of computing, we obtain the program which will drive the whole spacesuit, and that the astronaut can monitor with the LCD screen and this joystick.
Concerning gloves and boots, making handmade boots and gloves is very difficult because they have to be resistant, they have to be airtight, they have to be comfortable at the same time. So we decided to reuse gloves and boots from an existing safety suit for toxic environment. We reinforced them with Kevlar and rubber, and to improve the prehension, we also use silicone elements. Also, metal rings ensure the airtight connection with the rest of the spacesuit.
All right. One of the other particularities of a pressurized spacesuit compared to an analog spacesuit is that you have a limited volume inside. What I mean is that if you try to make that kind of movement, you will reduce the volume, the inside volume of the spacesuit. Therefore, you will increase the pressure, and it will be very difficult to move. So you need to use what is called circular bellows, which is roughly this kind of tubes. And they have the particularity to always have the same volume no matter how you fold them. So we worked with a private company to make 2 of these for that part of the arm and 2 of these for the knees. And we adapted them to the spacesuit with, once again, these small metal rings.
So the final process of this work was to put all these pieces together.
Well, even if we anticipated most of the issues that we might have, still something didn't work properly because some pieces were, like slightly too big. This is like 2 a.m. in the morning. We are super tired. We are about to place the last piece of the 200 pieces puzzle and something just wrong. But eventually, during the next 2 days, we reprinted these elements that had mistakes, and we adapted them to the spacesuit, and it worked properly. So it shows that 3D printing is actually a viable solution, because if you want to do that on Mars, you can. Yeah, we were supposed to have a video, but it's not working on that computer, so we'll go about the future.
What's next? So we now, as you may have seen on the picture, the spacesuit is not finished yet. We have to finish one airtight layer, and we also have to put the visor on. So this work will be done by the end of November, and then in December, we will deploy our spacesuit in the desert of Utah during the MDRS 185 mission. So there we will try our spacesuit in close to real conditions, and we will determine whether or not it's easy to maintain and to repair the spacesuit in a Martian environment.
All right, so that is pretty all what we wanted to share with you today. So if you have questions, feel free to ask. Yes, sir.
So one of the hallmarks of field exploration is having a meal regularly. Just wondering, did you guys do anything different than these in terms of being able to regularly touch the ground?
Yeah.
You mentioned the gloves and some of that. How about these?
Well, for the knees, we have, as we said, circular belows that are placed right here. And we have these, if I come back to the top, we have these simple plastic rigid elements also underneath, like here. We have 2 of them on the astronaut and 2 of them inside the spacesuit between the Kevlar and the dralon. So even if the dralon might be a little bit teared up, I don't know if it's the proper word, then it's quite solid actually. Yes?
Great job.
Thank you.
So what's the total weight, and how difficult is it to wear? How long does it take to don the spacesuit and to duff it? And so next year we're actually doing a full immersive Martian simulation in Kilimanjaro and up to Everest. So we'd be
Wow.
ready to test it out.
All right, so you want to answer, Anna?
So I don't know the weight in pounds, but
Well, yeah, in pounds. So yeah, in pounds it will be roughly 100 pounds, which is a lot, but it's for Martian gravity. So on Mars it would be roughly 40 pounds, which is, easy to wear. On the Earth, yeah, it's quite heavy, especially because I'm like 130 pounds, so the spacesuit is almost the same weight as I am, and I'm not like super strong. Yes, so it's kind of difficult, but still we can move, and we did EVAs up to 1 hour without any problem.
and even if the spacesuit will weigh 50 kilograms on Earth, it will only weigh
Yeah.
50 kilograms.
Yeah, we wanted something for Mars.
Total cost?
The total cost, it's in euros. We paid 4,800 euros for all the elements, and we will probably need 1 more 1,000 euros for finishing the airtight layer. So, yeah.
So I know you said you consider like the layers of your material, like at the
Yeah.
dry low or were you able to do you study or consider how like on Mars you would get extreme temperatures, like so because your material would get very brittle, it's very cold, and it gets hot like soon after. Do you test any kind of like thermal materials handle that?
No, up to now we only work with average Martian temperatures and conditions, because our model is not good enough to work with dynamic environments. So what we obtain here, that the average temperature will be 30 Celsius degrees for the astronauts, which means that depending on the solar exposition, it might be higher or lower, but still in general we will need to cool down the astronauts.
You had one of your criteria was to be flexible, but how did you really kind of measure
So I tried it now 4 or 5 times, and I have to say that it's quite difficult to kneel properly. It's easy to kneel, but it's difficult to stand up because it's like heavy. But still, I can do it with no problem. I can climb stairs up and go downstairs, and I can work on my, I don't know, with hands and knees on the ground. And for this, with Earth's gravity, it's once again difficult to stand up, but still possible. So on Mars, it should be easy.
That was pressurized, you did it? You've been in it pressurized.
Yeah, we want it to be pressurized, but we still have to finish the airtight layers. You have them for, we did them for the rear part. This one is now airtight. This one will be airtight by the end of October, and the whole spacesuit will be airtight by the end of November. Because it's like sewing hours and hours to avoid all the small leaks.
You're printing this in what?
Sorry?
You're printing this nylon, what material are you printing it in?
The material, the plastic for printing is PLA, which is quite basic as plastic. But we had difficulties, we had a limited budget, so we had to do it with PLA or ABS. PLA is better. But we have samples of other types of plastics, including Kevlar or carbon fibers.
Or even nylon.
Yeah, so it's very expensive, and we just use samples to try it, but we don't have enough money to make like a whole spacesuit with that kind of plastics. Yes? So we thought at the toilets, so actually we have diapers, I never use them, not yet. But it's actually a fun question because the school gave us a grant, but we did not receive the money on our bank accounts. Every time we needed an element, we had to go to the top administration secretary of the school to ask for it. And yeah, if you never ask your boss to buy you 20 adult diapers, then it's something worth trying. You probably never had this weird feeling. Yes, sir?
So, the greatest challenge for flexibility in the spacesuit is the fact that when it's pressurized, it moves to the position of maximum volume.
Yes, absolutely, like this, right?
And then to assess flexibility, you have to analyze volume change.
Yeah. So
in your assessment of flexibility, how did you include that?
well, we have actually these elements that you see here. These are metal strings, so they do not extend. And we have they are linked on one end to the gloves themselves, and on the other hand, they are linked to the shoulder, which is rigid because it's a rigid torso. So you cannot extend the arm, and it's the same for the leg. So you avoid losing your gloves or boots just because of the pressure.
So did you speak to any astronauts with spacesuit experience or people who worked with pressurized spacesuits?
Yeah, so we talked at the beginning of the project with Michel Tognini, which is a French astronaut who flew with the space station. And we will probably meet another French astronaut. I can't tell them now, but he's a friend of our tutor, and he will be visiting us in October or November because he will be doing a talk at our school, and we'll visit the labs after. And he's okay to try the gloves.
Okay. Yeah, a good idea is to try the gloves in a glove box where it's safe. You don't have to pressurize the whole suit.
Yeah.
So the chief scientist at my company is an astronaut with 16 hours of EVA experience.
Wow.
If you're interested in talking to him, he'd be delighted to invite you over,
Yeah,
over Zoom, if you want.
all right. We would be really happy to have his feedback about the problem.
Yeah, so he describes getting out of an EVA. He did an 8-hour EVA on ISS, completely black and blue
Yeah.
and beat up, unable to move his arms for the next day.
Yeah.
It's a flexibility issue is a really big issue.
All right.
And he's a 4th-degree black belt.
All right. Well, I'm not. I mean, not yet. Yes, sir.
What percentage would you say you were actually able to 3D print, and how much was other components like these tubes and things?
Oh, that is a good question. Well, the 3D printed parts weigh 23 kilos, and the total is 50 kilos with the air bottle. So it's roughly 46%, roughly a half. Half of it will be printed.
What is the cost comparison from one suit to what a suit costs?
Well, a suit like the Z2 from NASA would be roughly $5 million. Ours would be like $10,000. So it's like a huge difference. However, it's once again a student project. So here it's quite advanced, but you don't want to go to Mars with it without further trials and tests in vacuum chambers. So this technology might be, and will probably be, in the end, less expensive than traditional spacesuits, but still we have to do further testing before allowing someone to go in space with it.
But still, there will be significant.
We assume that it would be less expensive.
How comparable is this to Final Frontier?
Sorry?
Final Frontier? Final Frontier, they actually have pressurized suits for the
I don't see which one it is. Arno?
Final Frontier, is it? Yeah, they're like, they actually
It's the spacesuit designed to Mars.
well, it's pressurized, so it's pressurized, right?
Yeah, they
Have
So
you
you have
seen
to
any
compare-
suits to compare it to?
Comparing your pressurized suit to what's currently out
Yeah,
there.
so we compare.
Final Frontier.
Yeah, we compared it with the element that we had for the Z family of NASA, and we also went to the Air and Space Museum of Paris, where they have Orlan suits, Russian Orlan suits, 2 of them, and we made some comparison with them. But Orlan is for like flying in space. This is a field spacesuit, so it's difficult. When I was in Washington last year, I saw the Apollo 13 suit from the commander, which never went, obviously, to the moon. But it's difficult to compare because it's like really different technologies.
Well, you should actually check out Final Frontier because they've actually done a lot of zero gravity testing of their suits.
All right, we will check that. Thank you. Maybe we have one last question.
Are y'all planning on taking this into a vacuum chamber with somebody in it?
No, we are not. We will try to put it in a vacuum chamber before the end of the year 2018, but not with someone inside because it's way too dangerous. However, if you are interested in that spacesuit, all the plans and 3D files will be available for free on the internet before the end of the year 2018. So if you are a teacher with students at the university or in high school and with a lot of 3D printers, you will be able to reproduce it like for free, and we will be pleased to give you tips and advice to do so. All right, so thank you very much.